Hi, I'm Henry Sullivan, Chief Product Officer at Building Momentum. We provide intensive hands-on training programs for commercial enterprises and every branch of the US military. Our programs focus on emerging technologies and their real-world applications, such as 3D printing for drone design and manufacturing. Through our partnership with Formlabs, we offer end-to-end solutions for developing customized, high-performance, unmanned aerial, ground, surface, and underwater systems. Today, we'll examine two key 3D printing technologies, stereolithography and selective laser sintering. We'll discuss leveraging each fabrication method to design and produce durable mission-ready drones. We'll also cover critical assembly techniques, choosing the correct fabrication method for various unmanned systems, and a step-by-step workflow for our custom 7.5-inch SLS printed drone. Today, unmanned systems are deployed worldwide for a broad spectrum of applications. Despite the variety of drones in service, all designers and manufacturers must address several key considerations. Drones must balance structural strength with minimal weight. Lighter drones extend operational range and endurance, but reducing the weight too much can compromise durability. Tethered drones, which have continuous power, can be prioritized in heavier payloads like high-quality cameras or gimbals, while untethered drones must carefully manage weight to optimize performance. Traditional FPV drones rely on laminated sheets of carbon fiber for their frames, which offer excellent strength-to-weight ratios, but can limit design complexity and agility due to the constrained fabrication methods. These frames are well suited for consumer FPV drones, but less ideal for advanced UAVs. And when manufacturers stop producing certain components, you lose the ability to repair or modify your drone on the fly. Using 3D printing to design and produce drones allows you to make improvements, modifications, and repairs on the go, without slowing down operations. SLA 3D printing offers the greatest material variety and specialized properties like impact resistance, high temperature tolerance, rigidity, and electrostatic dissipation. SLS 3D printing, with materials like Formlabs Nylon 12 Tough Powder, creates lightweight, high-strength parts ideal for mission-critical applications. The self-supporting nature of SLS printing enables complex, organic structures that traditional machining simply cannot achieve. These materials are perfect for drone frames, enclosures, brackets, and sensor housings. Environmental exposure is a primary concern in drone design and fabrication. Drones operate in a diverse range of conditions, from harsh sunlight to heavy rain, and even fully submerged environments. Ensuring durability against UV exposure and moisture is critical for long-term reliability. Like any plastic, 3D printed materials can degrade over time due to prolonged UV exposure, which occurs in nearly every single drone application. Moisture resistance is equally important, not only for drones operating in rain or high humidity environments, but also for unmanned underwater systems that face continuous water pressure. SLA 3D printed parts are fully isotropic and inherently waterproof, making them ideal for sealed enclosures and submersible drone applications, even up to 5,000 psi, proving their viability for deep water applications. SLS 3D printed parts, while highly durable and lightweight, have a slightly porous structure that can absorb moisture over time, especially under pressure. However, post-processing techniques like cerakoting, vapor smoothing, or resin infiltration can significantly reduce water absorption, making SLS parts suitable for both aerial drones exposed to rain and humidity and underwater vehicles. Even without additional treatments, media-blasted SLS components perform well in most aerial applications, maintaining strength and integrity in challenging weather conditions. Drone production costs vary significantly depending on application, scale, and fabrication methods. Mass-produced FPV drones leverage economies of scale. But for defense, industrial, and specialized use cases, 3D printing enables an agile workflow that reduces lead times and shores up your supply chain. For consumer FPV drones, manufacturers can produce inexpensive injection molded or carbon fiber cut frames in high volumes, making it easy for hobbyists and professionals to access affordable, off-the-shelf parts. Customization at this level is often limited to small aftermarket modifications, which many achieve using entry-level FDM printers. For low to medium production volumes, 3D printing is often more cost-effective than traditional machining or injection molding, which can require expensive tooling. The Fuse series makes it possible to scale a 3D printing fleet like the one behind me for less than $100,000. For high volume production, injection molding becomes more viable. However, the high initial investments in tooling, often $10,000 to $50,000 or more, makes it cost-effective only for extremely large runs. Any design change at this stage requires additional tooling expenses, making it less flexible compared to additive manufacturing. In military and supply chain constrained environments, additive manufacturing bypasses traditional procurement bottlenecks, enabling on-demand, field-adaptable production without long lead times. A drone unit deployed in remote or contested areas can manufacture replacement parts for custom modifications in theater, ensuring continued mission readiness without waiting for centralized supply chains to deliver components. For a company developing a new drone platform, SLS 3D printing allows rapid prototyping, functional testing, and even initial small batch deployment before committing to mass production. By understanding production scale, cost constraints, and operational flexibility, drone manufacturers can determine the optimal balance between additive and traditional manufacturing methods to meet mission needs and budget requirements. Drones require careful electromagnetic interference and radio frequency management to ensure reliable communication, navigation, and sensor performance. Nylon 11 carbon fiber has been validated for EMI shielding and is currently used by major defense contractors for tactical unmanned aerial systems at scale. Formlabs also offers an open material license for the Fuse series, enabling experimentation with different sintered powders for specialized applications like RF transparency. These materials are ideal for enclosures and components requiring signal permeability, such as GPS housings, radio transparent domes, and sensor covers. TPU-90A, with its flexible properties, is especially useful for soft mounting RF-sensitive electronics, reducing vibration and ensuring clear signal reception. SLS is a fantastic platform for this drone frame. With the highly modular design that we've taken here, we can switch out arms, components as they break or need to be repaired. We've also got a highly customized design with the high power components up near the front, without any fear of affecting the sensitive RF components towards the back. We've also used the Nylon 12 tough powder, which is about the same weight for a 7.5-inch drone that you can get from another manufacturer, having similar properties in terms of stiffness and durability. So as you can see it here, this is the fully assembled drone, but in its frame components, this is everything, from the arms to the main body to all of the mounting. All of the other electronics inside are commercial off the shelf, with a fully NDA compliant stack, RC link. However, the digital VTX system is not NDA compliant. Now, let's walk through the assembly process for our custom SLS 3D printed drone and explore best practices for integrating additive manufactured components with off-the-shelf hardware. Almost every drone build, whether mass-produced, FPV, or customized, starts by connecting the motor arms to the base so that you can attach your stack. Dip your M3 screws in a tiny bit of Loctite, rather than applying the Loctite to the thread directly. Leave your screws slightly loose whilst you ensure alignment is correct, and then you can go back through and tighten them all down to create a tight fit. Here we've designed certain things for ease of assembly. The drone base has slots that capture the square nuts, so you can secure the arms without holding the nuts in place whilst you try and screw it together. The drone design is also fully parametric, so if you wanted to change one feature's size or shape, the rest of the drone will change accordingly. Mount stack onto mounting board. We use the flush mount screws with pre-designed countersink holes so that the screws will lay flat on the bottom of the mounting board and maintain a precise fit to all the assembled components. Install the VTX. Place the brass nut around the threaded SMA connector and tighten it to mount the antenna connector to the frame. Before positioning the video transmitter, or VTX, onto the frame, push the screws through the bottom of the mounting board so the holes match the mounting pattern of that specific VTX. Spacers are used to ensure there is an adequate airflow around or below the electronic speed controller to avoid overheating and damaging the component. Place spacers onto the screws and secure the VTX to the mounting board. The traditional placement of the video transmitter antenna is at the back of most drones, near items that are either susceptible to RF interference or could easily cause interference. 3D printing lets us customize this part, so we can place the VTX away from these risks, but that means we have to ensure correct cable lengths for both the camera and antenna to account for the longer distance between all components. TPU-90A powder is elastomeric and behaves like rubber, so it's excellent for vibration dampening components like this camera mount. Place your FPV camera mount, printed in the TPU-90A powder, on the mounting board and secure your camera with the small screws included in the VTX kit. Step 5. Mounting motors. Attaching the motor securely is essential. Use Loctite on the tips of your screws again and use a washer to distribute the force of the screw going through the nylon material. Keep the screws slightly loose, ensure proper alignment with all 4 of them in, then tighten fully. Add the nylon locking nut included with the motor onto the motor shaft, but keep it loose. It is good practice to organize your build by zip tying, electrical taping, or using wire channels to secure the motor wires to the drone arms, being sure to remove the slack when possible. This helps you to avoid mistakes in the assembly process and reduces the risk of a prop getting caught in a stray wire. Mount your ESC with the main power pads towards the front of your drone. This drone build was designed to be field serviceable, so your drone battery can serve as the power supply for a field soldering iron. Before soldering, apply just a little bit of flux to the pads to ensure a quality solder joint. We'll be using around 380 degrees C with a chisel tip. Add solder to the desired pad. Always apply heat to the pad, and then add the solder. Trim the wire to the desired length and wrap it around the screws for better organization. Then apply the tin motor wires to the pad. After completing motor wire soldering, prepare the cable connecting the ESC to the flight controller. Ensure that the connector properly attaches the correct pins of the flight controller to the correct pins of the ESC. Once the cable is validated, plug it into the ESC connector and just leave it there. Mount the GPS module into the TPU mount before connecting the supplied cable. Use a small tool to clear out some of the additional powder if needed. Push the UFL connector end of the RC receiver antenna through the hole in the underside of the TPU mount. You might need to use a small tool to push it all the way through. Cut one of the antenna holes on the backside of the TPU mount. This allows for the RC antenna to mount without breaking or bending. We've made this design able to fit multiple sizes of RC antennas. Twist the GPS cable so it's easier to push through the frame, helps reduce EMI, and adds a polished look to your drone. Feed the UFL connector through the hole at the rear of the mounting board to terminate where the RC receiver will live. Lastly, attach the RC receiver to the antenna. Be careful installing the UFL antenna as to not damage the connection. We're using the Ghost RC link, which comes with a locking UFL antenna, which makes the antenna a little bit more secure. We use a frame-mounted XD60 connector for easy connection and disconnection of the power source. Cut the 12-gauge red and black wire to length, appropriately strip and tin the ends, and solder one end to the XD60 connector. The flat side is positive. Add heat shrink to minimize the risk of short circuits. Next, mount the XD60 connector directly onto the frame using M3 hardware, and route the power cables back to the ESC. Solder the wires to the ESC's main power pads. Now we want to start the process of mounting the flight controller on top of the ESC. The ESC needs to talk to the flight controller to receive motor commands. Flip the flight controller upside down and place it onto the mounting screws so that it's easier to access the solder pads. Prepare solder pads to connect the GPS module by cleaning and tinning those pads. In addition to location information, the module also has a magnetic compass. That information comes from a different channel, and we need to make sure we're attaching the right wires to the right pads. Please refer to the manufacturer's pin/wiring guide to ensure proper connections. The radio that receives all the pilot commands also needs to be soldered to the flight controller. Tin the wires and ensure the proper pins are connected to the correct pads. For this particular flight controller, we need to solder together a set of jumper pads to use the raw battery voltage for powering the flight controller board. You can find these pads on the underside of the flight controller. Using the cable that was previously plugged into the ESC, attach the other end into the flight controller. Using the datasheets for both the flight controller and the VTX, make a cable that properly connects the two. Plug in that VTX cable as well. As required by the FAA, you must use a remote ID if you're flying commercially. You do not need this if you're flying recreationally under 250 grams. Many FPV consumer drones weigh 249 grams to avoid this regulatory hurdle. Attach the remote ID module by soldering the positive and negative wires to an available 5-volt and ground pin pair on the flight controller. Place the SLS printed cover on top of the mounted board. This design uses slots for airflow and cable routing. Route the remote ID power cable through one of these slots. Attach the FPV antenna. Place the propellers on the motors, secure them with nylon locking nuts, and tighten the nuts with a wrench. Secure the battery pack with Velcro straps and tape the balance lead of the battery out of the way so it doesn't get tangled or nicked by any of the propellers. By applying these design and assembly strategies, we ensure that our drone remains lightweight, durable, and easy to maintain while taking full advantage of the flexibility that additive manufacturing provides. To learn more about the Fuse Series SLS ecosystem, contact the Formlabs Aerospace and Defense team. To learn more about Building Momentum's custom additive manufacturing curriculum, including drone design, manufacturing, and operations, visit buildmo.com.